Thank you, Hank, for the invitation to talk in your seminar. So I will talk about the Muskat problem in subcritical Lp-Sobolev spaces today, and this is based on a recent joint work with my colleague Helmut Abels from Regensburg. So in the first part of the talk, I will introduce the mathematical model, and then in the second part, I will and present some general properties of it, and then in the second part, I will discuss the main result of the paper, which is a well-posedness result, and then I will present also some main steps in the proof. So let's get started with the mathematical model. The model was first proposed in 1934 by an American engineer, Maurice Muskat, to model the motion of two immiscible fluids, which are also non-Newtonian, such as oil and water in a porous medium. Porous media, these are composed of sandstones, and here you see cross-section through such a rock. The rock has small holes, and fluids may flow through these holes. And this is a model for the oil extraction process, and this is pictured in this image. So what you see here is a cross-section in the porous media in the XY plane. We have two impermeable layers, and between there's a porous media filled with water and oil. So water is located beneath usually, and oil is above. And in the first stage of oil extraction, the so-called primary recovery, the pressure is high enough for the oil production well to extract the oil at a quite fast rate. However, after some quantity of oil is extracted, the pressure in the system drops, and then usually engineers pump water in the water layer and increase the pressure in the domain, and then the production rate is kept at a fast. It's fast. So this is a secondary production, and the Muskat problem is a model for this secondary recovery, and this is what we modeled by the Muskat problem. So what one may think that if one pumps water at a fast rate, then the production rate is also fast, but this is wrong, because in this water oil business there are two issues. So the positive thing is that the density of water, which is the fluid below, is larger compared to that of the oil, and this stabilizes the process. However, water flows much faster than oil, and then if one injects water with a velocity too large, then viscous fingering may occur. There comes to a mixing of the two fluids, and this is what people do not want to extract a mixture of water and oil. And this viscous fingering is very nicely presented in this picture. What you see here is a so-called Hilly shot cell. It consists of two parallel transparent plates filled here with a transparent liquid. This is glycerol, and has a larger viscosity than water. Water is a fluid colored in red. And this fluid is injected in the middle of the cell, and because it has viscosity less than that of the glycerol, one can observe these snowflake structures occurring. One should mention also that in this setting, this Hilly shot cell is horizontal, so that gravity effects are neglected, are negligible. So let me first present the physical setting that we consider in this talk. So we consider a two-dimensional geometry, so 2D flows, and the fluid phases are assumed to be unbounded. We denote by minus the fluid locate, and they are not only unbounded, but fill the entire R2. So the lower fluid is denoted by minus and is separated from the fluid above by an sharp interface, which has parametrized at the graph of a function which f, which depends on time t and the position of variable x plus vt. And we assume here that this system moves with constant velocity, 0v. So if v is positive, both fluid phases are transported upwards. And this is what we model, how we model this injection and extraction of water, respectively oil. The fluids have general densities. They are denoted by rho, and also general viscosities, mu. And the motion is influenced by gravity. So we have here a vertical porous media. And we neglect in this talk the surface tension effects. So this is an idealized situation that we consider. And now let me present the equations of motion. So first of all, the densities of the fluids are assumed to be constant, and from the conservation of mass equation, we obtain that the divergence of the velocity field is 0 in the fluid layer. So these are the fluid layers located below or above the graph of F plus Vt. Yeah, I should also mention that F is also an unknown of the problem, and as you will see, this is the main unknown of the problem. Now, for fluids in porous media, the Reynolds number are small, and that's why one usually takes, instead of the Navier-Stokes equation, the Darcy's law, which is a linear relation between the velocity v and the gradient of u. U is a potential, is the sum of the pressure plus this hydrostatic term. And this Darcy's law says that fluid particles move from regions where the pressure is high to region where the pressure is low. They move vertically downwards due to effect of gravity. And the velocity amplitudes are large if the permeability is large, or if the viscosities are low. So if the fluids have low viscosity, then the velocities amplitudes are larger. These are the equations in the fluid layers, but of course we have also boundary conditions, and these are the natural boundary conditions. So we have the kinematic boundary conditions saying that capital V nu, this is a normal velocity of the graph. And this normal velocity should match the normal component of the velocity vectors of the velocities in each fluids on the boundary. So we have actually two relations. The velocity is continuous in normal direction, this interface, and we have the law describing how the interface evolves. Secondly, because surface tension is neglected, the dynamic boundary condition tells us that the pressure is continuous across the interface. And we have the far-field boundary condition, practically saying that far away from the origin, the fluids are transported with the velocity 0v. So the interface is flat and the velocity matches asymptotically for xy to infinity, this constant vector field 0v. These are the equations of motion, but it's natural to view this system in a moving coordinate frame which moves with the velocity 0v. So then the fluid domains would be located below or above the graph of F, and it is natural to define a new pressure and a new velocity cap P and respectively cap V by these formulas where we subtract here on the right-hand side this constant velocity field, meaning that cap V vanishes at infinity. And then we have written now the equation I presented above before in terms of cap P and cap V. And this is the evolution equation for F. You see a prime here. Prime means simply d over dx. This is a derivative with respect to the spatial variable. And because we have one evolution equation for F, we need an initial condition for F. So what you see here is that the first 6 equations or conditions are all linear and have constant coefficients. However, the evolution equation, however, is not linear. But because the function f is also an unknown, and the problem, the equation are defined in domains depending on f, this problem is in fact nonlinear, and we will treat it when solving it as being a fully nonlinear problem. So we deal with a moving boundary problem which with unknowns f, cap v, and cap p, but as you will see, f is the main unknown. We will treat this problem as being a fully nonlinear evolution problem for actually only f. And the important observation was that the equation, the first 6 equations consist of, are linear with respect to v and p, and in fact have constant coefficients. So questions one may ask when considering this problem for the first time is the type of the problem. You will see that the problem is parabolic, and we will use this parabolicity to prove well-posedness of the problem in Sobolev's LP-based Sobolev spaces WSP. And also other properties of the solution are interesting, such as the regularity. If the problem is parabolic, one would expect to have some smoothing, parabolic smoothing, and one is interested to determine criteria for global existence or for blow-up of solutions, and the existence and stability of stationary solutions is also an important issue to consider for this problem. And let me now say what kind of solution we are interested in. So P is a Sobolev index is strictly larger than 1 and less than infinity, and S is larger than 1 plus 1 over P and is less than 2. We look for solutions which are continuous up to t equals 0 in the Sobolev space WSP, and they are continuously differentiable in the Sobolev space WPS-1. So when we differentiate with respect to time, we use one order of regularity. This is because the problem is a first order evolution problem, and this kind of solution are called, we call strict solutions. The velocity should be continuous up to the boundary and continuously differentiable in the interior of the fluid layers. The pressure should be C1 up to the boundary, up to the interface, and C2 in the interior of the fluid layers. And in this general setting, it is important to introduce a further unknown, which we denote by omega bar. And this new variable measures the jump of the velocity at the interface in tangential direction. Remember, f prime is d over dx, so this is a vector pointing in tangential direction, and here is a scalar product in R2. So this new variable, for this new variable, we require that it belongs to WPS-1, and this is the natural space, because as you see, f is in WSP, and so f prime is in WS-1p, and there's no reason why we should require more or less. And now, why do we refer only to f as being the solution of the problem? One can use potential theory to determine V and P, the velocity and the pressure, from the first 6 equations in terms of F and this new variable omega bar. And this is something which was done first by Duchamp and Robert in '84 in the context of the Muskat problem with equal viscosity, so when mu minus equals mu plus. The advantage is that one gets rid of these 2 variables, v and p, but on the other hand, one obtains some singular integrals with kernels which depend on nonlinearly on f, and this makes the problem then in some sense more complex. So here is the result, saying that the velocity field is determined by the interface and this function omega bar. So let and this is a result established first in a paper from 2018 for p equal 2, but the result for p different from 2 is the proof is the same. So consider the global velocity field bold v, which is obtained by gluing v plus and v minus on this common interface y equal f. And then the result said that the velocity field cap v is defined by this integral, where the kernel depends on f, and we have the function omega bar here. In fact, this integral can be written down as an integral over the curve y equal f of x of a certain function phi of psi over psi minus z d psi, where z is xy, is a point in R2 with coordinates xy. So away from the interface, the velocity is defined by this formula. Phi is a function which has the same regularity as omega bar, and it depends not on psi, but only on the first coordinate on s. And clearly this function is real analytic in omega plus and omega minus, and due to the Plamet formula, one may consider the one-sided limits when of v plus and v minus on the interface. So the velocity field, this velocity field has limits, one-sided limits, which we denote by v plus and v minus on the interface, and they are given by the same formula as above, but now we have a principal value here. So what we do, we replace simply y by f of x, but now we have a principal value because this point z is a point on the interface. That is xf of x, and the integral is singular. So this kernel here behaves like 1 over s. So we have a singular integral, and then we have a jump of the velocity in tangential direction. So in normal direction, the velocity is continuous, but in tangential direction, we have a jump which is defined by this term. This is not all. From the equation, from the dynamic boundary condition and Darcy's law, one obtains an additional relation between omega bar and f. So this is a coupling. On the left-hand side, we have a constant and the x derivative of f. And on the right-hand side, we have omega bar plus, again, a singular integral operator with kernel defined in terms of f, and here we have omega bar. So the right-hand side is a linear operator in omega bar, but this operator is singular. And we have two constants here, a mu and c theta mu. A mu is related to the viscosities of the two fluids. And the important observation is that the absolute value of a mu is less than 1 if both viscosities are not 0. Then an important constant is a constant theta, which is a balance between density and viscosity. So we have this gravity term here, which is for the oil-water problem positive because rho minus is the density of water is larger. When we inject water, then V is positive, and we have here a negative term because mu minus is a viscosity of water, and water flows faster than oil. So this theta measures the balance between gravity and viscosity effects. And c theta mu, which we have on the left, is simply a positive constant. K is the permeability of the porous medium times theta. So, and now we recall the kinematic boundary condition, saying that, which is written down here once more, and then because we know the value of V on the interface, we obtain an evolution equation for F, expressed with the help of a singular integral. We have here the kernel from the previous side and omega bar. And this is a coupling between f prime and omega bar. because we have a single evolution equation, we have an initial condition for f naught. So f is assumed to be known at time t equals 0. And these equations are defined for x in R and positive times t. An important observation, okay, we use here a brief notation. We, on the previous slide, you have seen lots of terms, f of x minus f of x minus s, here, 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 they appear all over. So it's, we introduce a notation delta xyf is simply this difference, and then delta xyf appears always divided by y, and then this is how these differences appear here. So this is this makes the formula more compact, and you can write them on one line. So this is a Muskat problem. This is a contour integral formulation of the problem. An important observation is that if A mu is 0, that is when the fluids have equal viscosities, omega bar is a constant time f prime. And if we replace omega bar by this constant times f prime, here we obtain one single equation for f. So in the case of equal viscosity, is simpler because we do not have this coupling here. And in fact, in the case of equal viscosities, one can formulate the Muskat problem as a quasi-linear problem, which is not the case when the fluids have different viscosities. So let me now talk about critical spaces for this problem to motivate the choice of S on the previous slides. So if F is a solution to the problem, then one might easily check that also the function f lambda, where lambda is a positive constant defined by lambda to the power minus 1, f of lambda t lambda x, is also a solution to the Muskat problem, of course, to another initial data. And then one might ask which Sobolev seminorm is invariant with respect to this scaling. And then it turns out that if we take the first derivative of f and f of f lambda, and we compute the WRP, Sobolev seminorm with R equal 1p, we have inequality here. And this identifies the Sobolev space WPSC with critical exponent 1 plus 1 over p as a critical space of the Muskat problem. And our result will be in the setting when S is strictly larger than this exponent. So this is a setting where the interface is one-dimensional, but if the interface has dimension d, then this critical exponent would be 1 plus d over p. So with d, the dimension. So this problem is quite old, but the results on the problem are actually not so old, quite recent. Many results are very recent, and this problem has been considered in various geometries and with different approaches. On this slide, I have four groups which work with different techniques, and none of the list here of references is complete. So one has used, so E used in '96 Newton's iteration method to construct solution for the Muskat problem. There are people using Cauchy-Kovalevsky type theorems. There's a large group considering energy methods when studying this problem, and my research is in this fourth group who used abstract parabolic theories. So the idea is to formulate the Muskat problem as an evolution problem and to prove that the problem is parabolic. And for parabolic problems, there are actually, even for fully nonlinear problems, there are theories which work and which can be then applied to the setting, and then one obtains certain results which can be improved in this particular context. And in this side, we have some more recent results, which are in some sense covering all subcritical spaces. And the first result in this setting was by me from 2019, but in the simpler setting when the two fluids have equal viscosities. And that was a well-posedness result in L2-based Sobolev spaces HS with S larger than 3/2. So 3/2 is a critical exponent. I would also like to mention a paper with joint paper with Christoph Walker, where you're using a quasi-linear principle of linearized stability. We establish for the periodic problem, well, exponential stability of equilibria in this setting when neglecting surface tension, always flat interfaces, and they are exponentially stable in the periodic case. There exists a recent extension of the result to include homogeneous Sobolev spaces by Lazar and Al-Azhar. And I would also like to cite these two papers of Lazar from 2020, where he considers, together with different collaborators, the Muskat problem in the critical Sobolev spaces in 1 dimension and 2 dimension. I think Omar will talk next week about these papers. And there is also a very recent paper of Nguyen and Posader from 2020, where they consider a general setting of fluid with different viscosities, and they establish well-posedness in L2-based subcritical spaces and in any dimension. So D is larger equal 1. Related to this, there is a paper of Flynn and Nguyen who considers the Muskat problem with surface tension. This problem has the same critical space as a problem without surface tension, and they consider the issue of convergence of solution when letting the surface tension parameter vanish. So today I will talk about the paper with Helmut, where we establish in dimension 1 well-posedness in WSP, where S is larger than the critical exponent 1 + 1 over P. This setting of LP-based Sobolev spaces was considered before only in this reference, where the authors consider initial data in W2P intersected with L2 and in the setting of equal viscosities. So let me say something about the abstract parabolic theory which we use. This is this is nicely presented in Alessandra Lunardi's manuscript for 95, and is actually due to the theory is due to her. We will not present the theory in the full generality, but just as we use it here for the Muskat problem. So we consider an abstract evolution problem. The time derivative of f equals a nonlinear operator evaluated f of t, where phi is defined on an open subset of a Banach space E1 and is real analytic in a Banach space E0. C2 minus regularity would be enough here. And E1 is densely embedded in E0. These are both Banach spaces. And this evolution problem should be parabolic in the sense that if we consider the Fresher derivative of phi at f as an unbounded operator in E0 with domain E1, then this operator should generate an analytic semigroup in the bounded operators from E0 to E0. And for the parabolic theory of Lunardi, the following singular Horder spaces are very useful. These are the spaces C alpha alpha consist of bounded functions into E1, and they have the property that t to the power alpha f of t is an element of the Hölder space C alpha. So it is easy to see that the Hölder space C alpha is a subset of the singular Hölder space C alpha alpha, and these spaces are very useful because generators of analytic semigroups have maximal regularity in this type of spaces. Okay, and the result of Alessandra Lunardi says that for each F naught for each initial data in this open space subset O, the problem has a unique strict solution, which also belongs to some singular Hölder space C alpha alpha, where alpha is a priori fixed. So the uniqueness does not hold in our theory in the setting of strict solutions, but in the smaller class of strict solutions which belong to some singular Hölder space C beta beta. But the good news is that beta can be chosen arbitrarily small. And this is something which can be used for the Muskat problem to obtain uniqueness in the setting of strict solutions. Okay, this solution can be extended to a maximal solution. And this maximal solution depends continuously on F naught. So this is a classical well-posedness result. And finally, the semi-flow map, which maps the time and the initial data to the solution, is real analytic on the set where the time is positive. And this property, together with a parameter trick used often in parabolic problems, shows here that there is a parabolic smoothing property for the Muskat problem. So let me show you how to formulate the Muskat problem as a fully nonlinear evolution problem. So remember, we have the evolution equation for F and the coupling condition. Now the singular operator in the evolution equation for F will be denoted by B of F. It's linear with respect to omega bar. And the singular operator from the coupling relation will be denoted by A of F. And the idea is to show that 1 plus A mu A of F is an isomorphism from WPS-1 to itself. And if this would be the case, then we can invert this equation and determine omega bar explicitly in terms of F. And then we plug in omega bar in the evolution equation, and we are left with an equation of the type df over dt is phi of f, and phi of f is this operator. So instead of omega, we put this minus c theta mu, and this is the inverse of this operator by f prime. This property holds for all f in WSP. So this operator can be defined actually on whole WSP, but the property that its Frechet derivative is a generator holds for a certain open subset of WSP. And I will present this, I will introduce this open subset in this slide. So an important condition for the Muskat problem is the Rayleigh-Taylor condition, RT short, which says that the gradient of the pressure should have a negative jump in normal direction at the interface. So in this setting, the Rayleigh-Taylor condition is equivalent to two relations. So the first relation is that this constant theta should be positive. So remember, this quantity is for the water oil problem positive. This constant is negative, and this condition identifies actually largest value for V, above which theta is negative, and below V, the Rayleigh-Taylor condition would hold. But there is a second relation, and this is a relation related A mu to F. And here you see this operators, this is up to a constant, simply the nonlinearity phi of F. And because this lives in WPS-1, this vanishes in particular at infinity. So, and because phi is continuous, one can show that the condition that this function is positive identifies an open subset of WSP. So O These are the function for which the Rayleigh-Taylor function is positive. This is an open subset in WSP, and this is a set where the problem is parabolic. In the set, the condition that theta is positive has been identified previously within the linear theory by Suffman and Taylor in a paper from '58. And if the viscosities of the fluids are equal, then the Rayleigh-Taylor condition simply says that the fluid below should have a larger density. And this can be seen because equal viscosities mean a mu 0, so this function vanishes, this term also vanishes, and we are left with this condition, rho minus should be larger than rho plus. And here's a well-posedness result. We fix a p strictly larger than 1, less than infinity, and s to be larger than the critical exponent. And we assume that theta is positive, so Rayleigh-Taylor holds. Then for each f naught in O, in the set O, the problem has a unique maximal solution. This is a strict solution. Of course, this solution belongs to some singular Hölder space alpha alpha into E1, but uniqueness holds within the set of classical solutions. And we have that all f depends also continuously on the initial data. And we have, as a second result, a parabolic smoothing property that for the map Tx goes to f of Tx is real analytic for positive times. So this means in particular that f of t, the interface, is a real analytic function for all t positive. And we have a second property saying that the interface is real analytic for positive times into the Sobolev space WKP, whatever k is. So we have two smoothing, parabolic smoothing property, which are consequences of this result about real analyticity of the semi-flow map within Lunardi theory. So the main step in the proof is, of course, first establish that AF and BF map WS-1P to WS-1P. But then the first important step is to prove that this operator is an isomorphism. And this is only possible because A mu, the absolute value, is less equal to 1. Then one has to show mapping properties for this map phi, in fact, from WSP to WS-1P. O is here not important. And then the last step is to show that the Fresher derivative at F, when F belongs to O, generates an analytic semigroup in this space. And this is the only place where one needs the Rayleigh-Taylor condition. So I will say something to each of these 3 points. So for the mapping properties, we use an abstract result from harmonic analysis, which is an L2 result from 86 due to Murray. And he considers a Lipschitz function A from R to R, and associated to this function a singular integral operator TA, which is defined by this kernel. So if A would be constant, then if A would be linear or constant, this would be a simple constant, and this would be the Hilbert transform. However, A is allowed to be a general Lipschitz function. And the result says that then this operator maps L2 to L2, and its norm is bounded by a universal constant times 1 plus the supremum norm of A prime. And this is the last final result in a series of papers where similar results are established with exponents 5 and then later 3, and 1 is a limit case. So this is an L2 result, is not useful in the LP setting, but this result holds also in the LP setting. So whatever P is between 1 and infinity, TA is bounded from LP to LP, and its norm is bounded by the same thing. Only the constant is different, but the constant depends only on P. And the way to prove it is by a strategy which is nicely outlined in the lecture notes of Helmut from 2011. So the first step is to show that TA satisfies the weak type 1-1 estimate. So singular integrals are not, operators are not bounded from L1 to L1, but from the L1 to the larger space L1 weak. And this is how the L1 weak norm of TAH is defined. So as you see, we obtain that this operator is bounded from L1 to L1 weak, and the norm is exactly as before in the L2 case. And then one can use the result of Murray and the Marcinkiewicz interpolation theorem to prove the desired result for P between 1 and 2. And for P larger than 2, the result follows by duality, because the L2 adjoint of TA is minus T minus A. And this operator, we understand it very well now. And having this result, one can establish many useful mapping properties. There are also other results needed, but this is one of the main results in this first step. Then the next step is to show that this operator 1 plus A mu AF is an isomorphism from WPS-1 to WPS-1. In fact, the first step is to show that this operator is an isomorphism from LP to LP. So this is the main step. Having shown this, then this property follows rather easily. And the argument for P different from 2 is quite complicated. I will present here the result for P equal 2 because this result, this proof is very elegant. So remember, the velocity field on the interface is given by this formula, depending on where we approach the interface, from below or above. We have a jump here. And if we consider the tangential component of V, this tangential component can be expressed with the help of A. So it's A minus plus 1 applied to omega bar. The normal component of the velocity can be expressed with the help of B. And here we have these two facts and the following properties. So if F and omega bar are smooth and have compact support, one can justify the following computation. So we have here a field, we take the divergence of it, and because the velocity is not only divergence free but also rotational, the velocity is potential, then this integral is 0. So actually these two integrals, we integrate over omega plus or omega minus. These two integrals are 0. And using Stokes' theorem, we obtain two equations on the boundary. And these are the so-called Rayleigh formulas. And here is a Rayleigh formula once more. So we do not need to bother about F prime because F prime is bounded. Here we have the L2 norm of B evaluated at omega bar, and here is the norm of A minus plus 1 evaluated at omega bar. And here we have a mixed term, so F prime is no problem. And this term can be estimated by using Hölder's inequality and Young's inequality. And then from this equation, one obtains the estimate saying that A minus plus 1 at omega L2 norm is less than the constant times the L2 norm of B evaluated at omega bar. Now, if we build the difference of these two terms, then this is twice omega. So from this relation, we immediately obtain that the L2 norm of omega is less than the L2 norm of B evaluated at omega. And this property is very important because some elementary algebraic manipulation, which are quarter of a page, lead to the following second Rayleigh formula, where on the left-hand side we have the L2 norm of omega multiplied with this constant. This constant is positive if lambda square is larger than 2. Lambda square is larger than 1. we would like to consider to prove the result for lambda square larger or equal to 1, but larger than 1 would also do, because remember a mu is less than 1. But we can prove intervertibility also in the case when lambda is plus or minus 1. So this is positive or 0. This term gives when lambda square is equal 1 can be used to show that can be bounded from below by omega bar. And now let us check the right hand side. We have the norm of lambda minus a evaluated at omega, the L2 norm, and the mixed term. But the mixed term is not important, because by using Hölder and Young, the term with b can be absorbed with a small constant within this term, and the term with a can be absorbed in this term. So at the end, we obtain this result, this estimate, which holds for all omega bar in L2 and for all lambda, such that lambda square is larger equal than 1. And because A maps L2 to L2, if lambda is very large, this operator is an isomorphism. And then because of the estimate, the method of the continuity says that this operator is an isomorphism for all lambda, such that lambda square is larger than 1. For p different than 2, the bad news is that Rayleigh's formula has no LP version. So we have to proceed differently. The proof is involved. I will not say too much about it, but a crucial step is to show the injectivity of this operator. And for the injectivity, we have two different proofs, again, depending on whether p is less than 2 or larger than 2. Okay, and then the last thing to check is that the Fresher derivative of phi at f0 is the generator of an analytic semigroup in WPS minus, in the bounded operator from WPS minus 1 to, in the bounded operator on WPS minus 1 for each f naught in O, that is such that the Rayleigh-Taylor condition holds. And here's where the Rayleigh-Taylor condition is crucial for. The proof is quite involved, and it's based on a localization procedure. We will approximate this operator locally by certain Fourier multipliers. But this localization procedure requires some finite epsilon partitions of unity. And this works here because we can choose a partition with finite elements, pi j epsilon. So actually pi j epsilon squared is a partition of unity. So this partition has an element pi n epsilon. This is the function in red, which is 0 around 0. The support is contained in the set where the absolute value of x is larger than 1 over epsilon, and epsilon will be chosen very small. So with the help of p epsilon n, we localize at infinity, because functioning WPS minus 1 of R, they vanish at infinity. So, and then we have a lot of function with a small support, which are in green. However small epsilon is, we have finitely many of these functions. And we cannot, it is not sufficient to localize this operator, but we need to localize a continuous path, psi of tau, which relates the Fresher derivative to a simpler operator. This is a Hilbert transform. Here is a Rayleigh-Taylor function for f naught, and this is d over dx. So for example, if f naught is 0, then this operator is a Fourier multiplier with symbol minus absolute value of psi. And this is a generator of an analytic semigroup. So we need to do this because we need to show that this operator is, the Fresher derivative has in the resolvent set a certain positive, some positive real number. And this property can be carried by using the method of the principle of analytic continuity, of the principle of continuation. from the corresponding property of psi 0. Psi 0 is a simple operator for which we can show that it contains in the resolvent set some positive real number. And here is a technical result saying how we localize this operator. So mu is a small constant which is given, S prime is less than S, and the result said that we can find epsilon sufficiently small such that psi of tau evaluated at F can be locally approximated by an operator aj tau evaluated at pi j epsilon F, in the sense that this difference is smaller than this small constant, and here is a full norm, the norm in WSP, and here we have a larger constant, but the norm here is with an exponent S prime less than S. And aj tau are some Fourier multipliers which we understand very, very well. So we have here d over dx. This is a bounded function. B tau is a function who's bounded by a constant which depends only on f naught. And it's important that this coefficient have a sign. They are positive, namely alpha tau. We have here the Rayleigh-Taylor function for f naught. We have this positive constant, theta is positive, and this difference here is also positive. So these operators generate all such analytic semigroups, and then there is a technique to show that also the Fresher derivative of phi evaluated at f naught is a generator of an analytic semigroup. So today I discussed the Muskat problem in this subcritical Lp-Sobolev spaces, and this is a preprint where you can find more details. So thank you very much for your attention.